sort of jump right in and assume that everyone else will catch up. So the homework is, I guess, a little vague in terms of when homework is due, because it says today. I guess it says today. Was it midnight? Is it beforehand? Is it whatever? I'm not too worried. I know a lot of people don't have it in yet. So, and there was, it took me a little bit longer to get out a version that I thought was kind of, well, hopefully straightforward enough. So whether it's by the end of today or sometime before next class, that's totally fine. Just be aware that we're going to, get us to the next one. The homework is, there's not a lot of heavy lifting really in the homework. It's mostly, again, sort of like some, general questions about stuff we covered in class. Some of them, some of you may have noticed, there's some subtlety to them, in terms of, the multiple choices and so on. So it's not super trivial necessarily. And the big one for this particular homework is that you need to really do a transformation. Now, I'm not so concerned about you, really doing out every step of, the transformation, by hand or something like that. The real goal I have is for you to, just go through the process at least once. So if you look at the homework, and let's see, I guess I got to continue this. It's the last question here, and there's a little document that talks about the new and improved version of the sandbox, where that lives. You don't have to actually, get a version via GitHub Classroom, because there's just one version up there right now. My repository, you can grab that from. I'm going to try to keep that one a little bit more live and fun. And the goal is to sort of recreate this image. It may not be exactly that image because of, you might scale the window or something like that, and it's going to look a little bit off. But generally, it's going to be pretty close to this. You'll notice here, I've kind of blurred out some things for you to kind of play around with. There's a bunch of code already in there for you. Chances are when you first run it, it's going to do, there's going to be a red box that just kind of zips around because it's looking at some extra variables it doesn't need to, so you have to decide which portions of the shader can you sort of cut out, and it'll wind up looking something like this, except not blurry. You'll have your own versions of that. And there's a bunch of clues in this image here, and even in this image here. You pay close attention. I tend to leave lots of breadcrumbs around. But the transformation I want you to do, it says, let's look at an example. But by example, I mean this is the one we want to do for the homework. So you should be doing this set of 3 transformations, pretty simple ones. It's a scaling by 5 in x, y, and z, a z rotation of 30 degrees, and a transformation 2, 1, negative 2. So you're going to, sort of pseudocode it here. Feel free to use an online calculator if you want to see the steps and all that, whether you want to calculate it all out one by one. The main piece is you should be able to say to yourself, okay, I generally know what I should be careful here. I'm going to zip around. You should generally know what a transformation matrix looks like, what a scaling matrix looks like, what a translation, where the translation in X, translation in Y, translation in Z. And then probably the trickiest one, refer back to the lecture notes or online to see, okay, how do I come up with how do I create a rotation matrix in the Z-axis 30 degrees? And you'll wind up with 3 different matrices, one for each of those transformations. And the biggest trick on it, I suppose, is really kind of what's going on with the order here, right? So it's a little, you can get a little bit sidetracked if you're not careful, because the order likes to be sort of backwards from what you might think. So you go through the exercise. That's why I also provided what it should look like when you're done. So you can say, oh, okay, try it one way. Did it wind up being backwards? Try it the other way. It should be forwards. If neither of those are right, it means something's wrong with your calculation to begin with. So, just to really give you a feeling for what the process is and to be aware of those orders of transformations and generally kind of what they look like before we forget about them entirely and do them all inside of GLM and in math libraries for us. So that's the purpose. Now, so you can figure out your matrices using whatever calculator, or do it by hand, or all the breadcrumbs are in the lecture notes, and certainly online if you want to use a calculator. And in the end, you'll wind up, if you have two choices. Suggest you go through kind of both of them. One, which is to download the whole repository and build it yourself. You can. And just as a safety net, I also provided a pre-compiled G4G1 exe, which if you run that, you'll get this. You won't have to compile anything. That's the joy of being able to change shaders on the fly. And I included a matrix that you can kind of set by hand there. So you can type in things. And okay, the first giveaway I'll give this part. All right, well, let's kind of get our square to settle down. And we can see the top shader here is our vertex shader, and the bottom shader is our fragment shader. We have a couple of buttons. We have the Use Shaders button, which just basically means whatever's in the current shaders, go ahead and use them, compile them, do the right thing. We have the Save Shaders button, which actually now is Save Shaders and this matrix. Right? So it'll save the current state of the shaders to files and save the matrix out to a file as well, so you have it to refer back to. Wonderful how convenient that is, so hopefully life is easier as a result of that. And there's also a Swap Texture button, which comes more into play as we start playing around with textures. We'll talk about textures a lot today. And as part of the homework, you wanted to basically kind of get the texture working, and you can kind of, hopefully, kind of figure out intuitively, I hope, from kind of the provided sample code where things might go. So let's just, as an example, say I want to settle down that shader, or settle down the square. First off, I notice in my shader I have this GL position. So the position, I'm passing in all my vertices, my vertex coordinates as this A position. If I look up here in my shader, I see that A position, or A pos, is at location 0 within my vertex attributes. And it is a vec3, so I can see kind of what's going on here. So now if I say use shaders, it settles down. And somebody online got a lot of noise going on? Just, I am paying attention. So got some kind of live mic online here. Evan, kind of hear you a lot there. No problem. One of the joys of this all now, right? So now you'll see in the shader, all right, it's not moving anymore. Why? Well, because we had this offset thing. And this is where it starts to come, useful to look at the code, even if you're not able to compile the code just yet. If you go into your program, into your actual source code for all of this, which similarly, let's see, sandbox, we wind up looking in the build directory, G4G build, and we can run the solution. All right. And this version is, it's actually a little bit more advanced than the other one, but the main thing we'll look for, it's still there. Okay. So if we look for something that says offset, right? We saw this offset here, and so let's do a search for offset. I'm a big fan of like forensic analysis, forensics, going in, and dissect cadavers and all that kind of great stuff. So we'll look for breadcrumbs throughout here, because that's kind of one of the key things to like figuring out most game engines and so on. Being able to kind of draw your own conclusions, figure out where things are, get into debugging and so on. So I was looking for some variable called offset, and I found, sure enough, that there is a line here, GL program uniform 1, which means I'm setting a uniform variable that we talked about last time, and I'm setting it for our shader ID, which is our shader program. It's the handle to the shader that we've compiled. And normally I would say, what is the location of the variable that I'm changing? In this case, we're just getting it right there. We're just saying, okay, GL, get uniform location, and we're looking for that offset uniform variable in our shader, and sending it the value that's in X, which is this handy, just kind of dynamically changing little static float that changes by some increment. So it jumps around, but slides back and forth on the screen. That's how we're dynamically changing it. Right, so we're not sending it any new vertex coordinates or anything like that. We're just changing this one float, and then in the shader, we're deciding, okay, what do we want to do with that float? In this case, we're just adding an offset to X, Y, and Z. So that's why it was kind of moving back and forth. Now, you probably noticed it certainly looked like it was moving in the X and Y direction, but it didn't move, or doesn't look like it's moving in the Z direction. Anyone have a guess as to why that is? Yes? It's what? It's basically an orthogonal view. It hasn't, there's no perspective transformation on it. Right, so we're just looking through sort of the default camera. Right? There's no perspective, there's no projective transformation. So by default, that would be an orthogonal view. So Z is flat. So if we want Z to have an effect, then we have to at least be somehow transforming, have that projective transform. Now, usually a projective transform will be a combination of the camera's position and the projection, so we're going to kind of add those two right here. All right, so you would have the option, you can always pre-calculate certain things over on the CPU side. So you want to combine the M, the V, and the P matrices all together over on the CPU side. We can do that and make one transformation for them. Or we can hand each one of them over to the shader and let the shader do whatever it wants. So because I don't want to recompile everything, I'm just going to go ahead, and I know, because I looked at the breadcrumbs, that there actually is a uniform matrix 4, right? These are transformations, transformation matrices. We always use matrix 4s. And we have a P matrix, one that's called PMAT, one that's called VMAT, and one that's called MMAT. They're already over there. We can find them if we want. We can go over here, and we'll see. Here's the perspective or projection matrix. Here is our V, which is our view. So our camera is offset a little bit there. And then, of course, there'd be a model, which down here we have some animated model matrices. We have a bunch of them that we can kind of choose from. They're kind of predefined, doing weird things for us. I think we just have basically MMAT and MMAT2 in the example program. I added an MMAT3 to do some tumbling, but we'll leave that. So over here, now here's our, we refer to this as MVP matrix, but it's sort of backwards, hint on the homework. So I'm going to go ahead and say PMAT times VMAT. So I build in those two. I'm going to say use shaders now. Oh, I got a bug. It said, oh, I just had a capital there. And voila! Suddenly, our square has changed size. And if we go back in and we build back in our transformation, or we could even do this. We could just say, let's only change the Z value. I guess it's far enough away in the view. Oh, that's interesting. It must be right at the edge of clipping, I guess. It's kind of a fun one. let's not animate it that way. Let's say use shaders. And now let's change here. We could say 3. Oh, well, for that one to work, we also have to say, well, let's bring a model matrix in, right? So last but not least, we'll use a model matrix. So now use shaders. So I have moved the model, the square, closer to me. I can move it further away again. Let's move it to 0. Let's move it to -1, -2, -3, -4, and so on. So it's further and further and further away from the camera. So yeah, having it flip between 0 and 1 is not all that useful. It needs to be pretty far away to have a real effect, which is why that's more. The offset one was kind of weird. So now we've moved the model into the screen 8 units. So that works now that we have a projection and a view matrix to help resolve that. All right. Now, in the version I have here, let's see, matrix 3. Oh, well, no, I don't actually have it in this one. So this is the pre-compiled, so that should just be matrix 2. And matrix 2. Okay, so there's a rotating transformation there. That happens to be the other one that's built in. And if we look at here for MAT2, you can see here, now this is another one, it's calculating it on the fly. This is calculating a whole matrix, not just calculating a changing float. Right? Offset was up here, which is just a float, a uniform 1F. That means it's one float that's in the uniform. Down here in matrix 2, we're actually using a full matrix, and we are using translate and rotate to kind of move the cube or move the square and then rotate it. You'll see it's using time, so incrementally rotating, and the axis it's using is just the z axis, 0, 0, 1, right? So it's rotating in z, which is why it's spinning around like that. All right. So the other neat thing it does is you'll notice here in the fragment shader there's a couple of different things you can kind of play around with. The first one that's commented out there, it is looking up a texture, so a fragment from a texture, according to the passed in texture coordinates. So if we enable that by uncommenting that out, we get our good old RPI seal there. So it's using a texture render. That, and the other one is we say swap, it has our texture that we're creating on the fly that we can create later on. All right. So for the homework, the key is going to be down here. What do you wind up plugging into the matrix here? And remember, this one is in mat, just mmat, right? So use mmat like that. Now we can move it around this way. 4, 3, 2, 1, -1, and so on. So this is just a 2D kind of square. It's a set of two triangles. Follows pretty closely from the first texture example that Learn OpenGL has. So whether it's the RPI seal or the other one, everything else is pretty similar. Okay. So that should be good for the homework. So let's talk, now get to sort of lecture material. Yes?
I was just going to ask, the purpose of the third column seems so clear to me. Like, in the first column, choose the one, it
Yep.
scale up an axis, the other scale up an axis. And the last one, same thing, except it scale up the third one. It, no matter how much you look at the projection, doesn't do, or at least not.
Where are we here? Is this one? So this is the X scale, the Y scale, and the Z scale. Right?
But if we change that number, then even if you Pmat, Nmat,
Right.
for the projection,
Yep.
nothing changes.
Right, because it's just a flat quad. Right? This isn't actually a 3D model. It's just two flat triangles. Right.
Okay. So then, sorry, follow-up question. What is the last column?
The last column, it enables us to do transformations. Excuse me, not transformations, translations. That's why we have an X, a Y, and a Z translation. Right? So we can move it using that column, whereas everything else is a rotation or a scale or some combination that allows us to do that. Okay. So that's one of the big reasons why we use 4x4 matrices, because we can do translations with them that way. Right? We can factor in everything about being able to have direction vectors versus points, and we can translate. Without that, it's kind of hard to do. Right, so that's the main bonus of that. I always forget. I think I have a bug in there. It's if you shrink, there must be a divide by 0 somehow as a result of shrinking the window. So I'll have to fix that. All right, any other questions? All right. So texture mapping, we've seen a little bit of it now, kind of hinted at that. So adding image data to the object surface, that's sort of the most basic. That's what we think of it like decaling or decaling. I don't know, some people, I think in England, you refer to it as decals instead of decals. But the basic idea, kind of, the original, after the moment we went after colored polygons, it was like, okay, how do we make something look more realistic? How do we add more detail to the image without adding actual geometry? The question is, well, why don't we just take image data and draw that on those polygons? Imagine a computer screen, right? Your computer screen, basically, you have some image that is mapped to the computer screen, so it's just flat on there, right? So the simplest case is adding image data to an object's surface according to some lookup, right? A UV coordinate lookup that we use. So an example, say we had a model of a dolphin that was made of triangle primitives. We could texture map that model using different textures. The first one being a checkerboard, a very odd-looking dolphin. But you can see, the mapping there. It's kind of, you get a hint as to the lookups that are going on. But then the proper texture map kind of looks like this kind of flattened dolphin, or at least certain parts of it are sort of flattened, because it is, most texturing that we do is a lookup into a 2D map, right? A 2D image usually. And for each vertex, there's a coordinate in that texture map, or each vertex has a coordinate to look up in the texture map. So it finds the right one, and it can map things the right way. Right? So there are several mechanisms that need to be coordinated to support texture mapping. You need to have a texture image, which holds the desired appearance. Right? It might be a PNG or a bitmap, or just a raw image or raw set of arrays in memory. a texture object that holds the texture image. Let's see. For now, in this chapter, in this piece of in this part of things, we're going to consider only 2D images. Most of the time, that's what we're dealing with. We can get into 3D textures as well, which we will in the future. There's also something called a sampler, and the sampler variable that we set up so that the fragment shader can access the texture. Right? There's a way to say, okay, given these coordinates, how to look it up. Right? So our sampler is the thing that tells us, that does sort of the mapping on the fly for us once we have the coordinates. We have a buffer that holds the texture coordinates. It can be either its own buffer, or it could be interleaved with other vertex attributes. And then we describe that as a vertex attribute so that the texture coordinates are understood by the pipeline. And there's another piece, a texture unit on the graphics card. In the simplest cases, where we're only doing simple texture mapping, you might even sort of ignore that part and it'll just automatically kind of fill that part in for you. But as you get into more complex uses of textures, like you're doing bump mapping or using textures for all sorts of different things, light mapping, shadow mapping, all that kind of stuff, then you start to deal with potentially multiple texture units, and you can coordinate that through your shaders and subject to the capabilities of your graphics card. Right. Now, if you're using the textbook or you've found the last semester's textbook, the Gordon Clevenger examples use the Soil 2 library for loading a texture image into an OpenGL texture object. And that library, if you are using Soil for some reason, and maybe in some example you find uses Soil, the nice thing about that is it has built in this capability to say, okay, load in the texture as if it was going to be using it for OpenGL, and you can just say, off you go. In our case, in the sandbox and Learn OpenGL, we use something called STBI, the simple blah, 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 image library. I can't remember off the top of my head now. It's also a common one. There's really only one little thing you need to do that kind of makes life a little bit easier, and that's you have to remember that textures are upside down compared to images. That's one of the real kind of sneak things about it. So you'll see this in our code. You see this STBI underscore set underscore flip underscore vertically on load true. All right, and that just tells it, okay, when you load this texture, flip it upside down for me, please. You'd be surprised how many courses I've seen where they just went the whole semester, didn't realize that was backwards, because textures, unless they have text in them or they have something obvious, you're just like, okay, it just looked okay. But that was one of the things, first things or not first, but found out in game architecture that the engine had been using it, all textures flipped the wrong way, which is why someone stopped using the RPI seal and went to other textures, but we fixed that now. So this is the setup for loading, and then once we have data, we can tell OpenGL the format. You'll notice now we have RGBA or RGB. Textures can be all sorts of different formats, 8-bit per component. They can support transparency, alpha or not. They can be compressed. There's built-in compression on now just, I think all graphics cards support the compressed texture formats. Some tools will automatically compress textures on the fly, do all sorts of things to save the amount of memory. It used to be a real resource hog on graphics cards when we weren't, it's more about the number of textures that you could have versus the number of vertices, because you could never possibly render that many vertices. But now that you can, now geometry is getting really, really complicated. Textures are becoming not as much an issue. So now we have really nice, crisp, here's the whole thing, oh, we're using 2K textures or 4K textures. And, now if you go to, I think it's, what is it, I'm forgetting the site that has all the wonderful textures on it. It's owned by Epic Games now, and they have all high-res textures and things on it. But anyway, so there's lots of different formats. This is the main one you run into now, RGBA, which is going to be 8 bits per component. So we can load a texture, tell OpenGL, yes, here's the data we want to use. So here's what we actually loaded. This is where it loads it into the CPU memory. This GL text image 2D is where the CPU tells the GPU, okay, here's the data here that you're going to use. And then it knows how to use it. It generates these things called MIP maps, which we'll talk about in a moment. So if you see MIP map, it's kind of an important step. And then once it's loaded onto the graphics card, the actual image data doesn't matter anymore, so we can throw that away. And so you can read a file in, decompress it, or have STB load it, give it to the graphics card, throw away the original, save space. Right? All right. Now, texture coordinates, UV coordinates, how do they actually work? How do they map? How do we get these square, what are usually square bitmaps or square textures, and use them with triangles, for example, or use them with complex meshes? Well, we have to think of them as varying from 0 to 1. So no matter what the size of the texture is, no matter what the resolution of the texture is, that's really resolved later. It just assumes that a texture is 0, 0 at one corner and 1, 1 at the opposite corner. Doesn't matter if it's rectangular, it doesn't matter if it's square, if it's even and so on. It's always a matter of 0, 0 to 1, 1. And each model vertex is going to have a texture coordinate that's set like that. So given the first model we have up here, specifically it's designed to be sort of broken. So you'll see it has 0, 0 at the lower left corner. And you would think if it wanted to texture it correctly, it would have 1, 1 at the upper right corner, but it doesn't. So we wind up with this kind of odd-looking sliced image down at the lower right, because it's not just using a direct mapping. Like if it decided to use for this 1, 1, if this had been 0, 1, and this is 0, 1 here, and this 1, 1 here, and this 1, 0 here, it would have done the right thing. So it's actually not that complex to figure out, for the simple cases at least. It's a little more intuitive than you would think. And get a feel for it after a while. If you've ever worked inside a program like, boy, I'm forgetting all my, not Maya, but, oh boy. There's various programs that excel at, doing the actual texture and texture mapping and texturing and unwrapping and so on. You can do it in Blender. Blender actually always has like everything. Blender does everything to some degree. Other things kind of specialize in doing something really, really great. But most 3D packages, authoring packages now have some means of doing the texture mapping and painting UV coordinates, UV paint. In the case of a triangle, it's actually not all that tricky. It's really just a matter of saying, all right, the base is at 0, 0, and 1, 0, right? And the top is somewhere halfway in between, and it will know to do the right thing. So if you wanted, for example, this pyramid, right, the set of coordinates for this would be, this one would be the halfway between, right, 0.5. Whereas, say, the bottom of the pyramid, which is a square, that one, it is important to have, similar mapping, the correct mapping version of this for the bottom. All right, so it's really not that bad to figure out, okay, what are these coordinates? It's just how does it look? Imagine flattening out or having, that particular piece of geometry, that triangle or that set of triangles forming a quad, and how would that map onto a flat surface? It doesn't have to be geometrically perfect either. It doesn't have to be a one-to-one relationship, right? You could actually stretch and squash and have, weird coordinates. Just because your triangle is a right triangle doesn't mean that the coordinates that you are looking up in your texture map need to also represent a right triangle. So you could get all kinds of crazy. You'll see some tutorials where they actually use very, very, very tiny texture maps with like 1 pixel per color. and do weird games like, set up the texture coordinates to really just kind of be pulling out things as if they were palettes. Right? So it's odd cases. It doesn't have to be a one-to-one relationship like this, but often you'll see that it is, for the typical use. So we have these texture coordinates. One method of getting them over to the GPU is to have another buffer, another VBO, that contains just the texture coordinates. So you could have a VBO that contains your vertex coordinates, you could have a VBO that contains your colors, you could have a VBO that contains your normals. You can have multiple VBOs. Or they can be interleaved with your other texture attributes like we were showing in, and I think the examples in the sandbox all are interleaved now, right? So you could say each texture contains, it's a single buffer. It has a texture coordinate, a vertex coordinate, a texture coordinate, a normal, and then the next one, and the next one, right? So it's an array of structures as opposed to a structure of arrays. Right. The typical kind of setup is to declare a sampler variable in the shader, which looks an awful lot like the setup there. This is for accessing texture unit 0. So if you don't do this, it will wind up assuming that texture 0 is where your sampler is mapped. So let's see, let me pull up here. You'll notice in here, we're not setting up a texture unit there, a sampler there, because we can assume that we can just use one. So if you're not specifying one, it'll assume the basic one. In the C application, associate the texture object with the texture unit. Now you will have to do this over on the CPU side because it definitely needs to know what texture, how you're passing a texture over there. Texture coordinates are in a vertex attribute over on this side. So for example, in our shader now, it's going to receive the texture coordinates after they pass through this side of the pipeline here, right? So we read in the texture coordinates, then we are just passing them straight through here. You can manipulate the texture coordinates just like you can manipulate any other coordinates in your shader, right? So you can even animate your textures or do all sorts of things. But ultimately, the vertex shader is sending the texture coordinates over to the fragment shader, and it is going to, just like an interpolated color, it's also going to interpolate the position so that when the fragment shader does look up the texture, as it's looking at our texture now, and it really is just assuming, like, without the set, because there is we didn't set what texture unit to use, we could really just use anything. 0 is the texture unit that's used by default. But in the end, it's a matter of looking up the color into the texture according to the sampler and the texture coordinate, right, which is going on here. The sampler was our texture, which just happens to be set here. We declare it uniform sampler to the our texture. Over on the fragment shader side, that's where it's looked up. The Learn OpenGL version also is pretty good. So, learnopenjoke.com, they have in their section here, setting up for basic triangle. Same sort of the basic pieces of it. All right. So it feels like that should be it, right? Texture, coordinates, look them up, away you go. Get the results kind of like this, right? You imagine taking a brick wall, and with the right coordinates, we can make a brick pyramid, or we can have what looks like a sky pyramid or something like that. There's a lot more to it, though, in terms of making textures look good. Back in the early days, of course, it was just everyone was, the moment you put textures on there, everyone was happy. All right, that's the minimum we can do. But you start to get into issues like, well, what is the resolution of the texture versus the resolution that you're presenting something on the screen? Or did you start off with a low resolution texture and your screen resolution is much higher? Or as you show a certain triangle on the screen, it's scaled in some interesting way. And all of those, if you're just looking up the texture, in a naive way, that can lead to all sorts of artifacts, right? Bad results, glitchy graphics on the screen. Right? So texture artifacts can occur when texture image resolution is too low. That's a common one, certainly in older games. Texture image resolution is too high, believe it or not. Yes, there is such a thing as having too high a resolution. And what does that actually mean? Well, why would that be a problem? That's because of something called sampling error. Now, if you've taken, has anyone taken a DSP course at all? No? Okay. Sampling, heard the term sampling in general? The idea, if in audio we hear a lot about sampling, sampling audio is the whole process of digitizing audio is basically sampling. Right, so we start off at some analog signal, like an analog audio wave, and we have to determine in order to digitize it, we have to digitize it at some frequency in order to represent that in the computer. Right, so we sample the signal, we put it into the computer at effectively some resolution. In the case of audio, you have an amplitude resolution and you have how fast you're sampling it according to time. Now, this example here shows a waveform. So you can imagine this is an audio sample. We're trying to sample some type of sine wave, right? And the sine wave there, imagine we have a very high frequency sine wave, right? We have a very high tone, very annoying pitch in our heads, and the sine wave is rising and falling, and it's at some frequency. There's some number of cycles per second in that sine wave, how fast it's rising and falling. And along we come and we decide to sample it. And we sample it at some interval here that is not a match for the actual frequency of the sine wave. So instead of sampling it right where it would cross, we just sample at some maybe arbitrary relationship. I mean, is it a fixed rate, but not a fixed relationship to the other sine wave? So we're sampling at an even interval here, but we wind up picking these values that, in the end, if we just connect the dots between those samples, we have a much, much, much lower frequency sine wave. Right? And so if we reconstructed that from there, we would have an entirely different sounding sine wave. Now the same thing happens when you're doing spatial sampling as opposed to just temporal sampling. Spatial sampling, an X and Y, right? Imagine a pattern like a checkerboard. What's happening is it's going between 0 and 1 at some frequency in both X and Y direction, and if you don't sample it according to the right resolution, if you sampled a checkerboard and you somehow wound up just off, you can imagine, for some weird reason, you wind up just hitting all the black squares on the checkerboard. So suddenly, instead of your checkerboard graphic, you wind up with something that looks like a black cube or black square. because you hit the wrong boundaries. So dealing with this sampling error is a real thing, right? So here's an example of aliasing in a texture, and you'll see what's happening is, as things get further and further out, you start to hit different boundaries you beat against the frequency of your texture, the resolution of your texture, versus how much you can actually sample across because of the resolution of the screen. So you get these weird kind of moire patterns and weird effects. And this also can cause kind of sparkling when objects are animated because they're moving against that grid. And sometimes things will pop out. You can imagine our case before where we had, just that if you had managed to sample that checkerboard just right to get a black square, and then you move it just enough, suddenly you might get an entirely white square. Move it just enough, it gets a black square again, and so on. Right, so that's what happens when you have aliasing. So one of the things you do to combat aliasing is this thing called MIP mapping. It's multiple image. I can't remember what MIP stands for now. The idea behind MIP mapping is that you quickly and automatically, in most cases, generate multiple resolutions of an image at smaller and smaller sizes, and then refer to that as your changing resolutions. Right? So we start off with the main image, and we store also the half size and the half of that 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 and so on. And it can be done in such a way that it only requires a third more of the storage for than the original image. So it's not necessarily as scary as it sounds when you talk about generating lots more versions of textures. But it can be very, very useful because then the graphics card and OpenGL can do the right thing, have the properly scaled version, so things kind of, black and white will then blur to gray in the background, right? Because you'll be sampling something that is a hopefully correctly filtered version of that image at a much better resolution. Right, so that's what's going on in this image here. Right? We're generating MIP maps, and we're also telling it how those MIP maps should be filtered, so how they're generated. So imagine we say, okay, bind this texture. Every time we want to use something, we bind it. And then we set some parameters for it. We say, okay, we want to use minimum filtering. We want to MIP map nearest neighbor filtering, and then generate the texture. There's lots of different parameters for filtering as well, depending on how powerful your graphics card are filtering. We'll talk about that in just a second. So then OpenGL will try to use the resolution in the MIP map closest to the region being drawn, closest to similar to that same size, right? So much better result. However, that still can have artifacts. It's not an ideal situation because you might be at a boundary, right? Suddenly you go from one to the other. You switch, okay, now I'm switching from that black and white checkerboard to a gray. Right at the edge, not so great. So we're better off, but it's not necessarily the perfect world. So there are different types of what we call minification filtering that can help with that. And what we're doing now is we're adjusting the different types of filtering techniques that it's using along boundaries, where it'll say, okay, at these boundary edges, do we want to average between the two, filter between the two, and so on. We have a number of different modes. Nearest, choosing a MIP map with the resolution most similar to the region, right? That's the simplest one. Then we have linear filtering, where we're going between two. So we're going to use 4 texels nearest the texture coordinate to some sort of averaging or blending between those two, so it doesn't have stark differences. Then you have bilinear, where you can look at the two neighboring and the nearest and filter across. Did I get that backwards? Choose the 2 MIP maps with resolutions nearest the region and interpolate between the two. And then trilinear, choose 2 MIP maps with resolution nearest. one of them should be reflecting the third. Come back to that one. The trilinear one is wrong. But different types of filtering, we'll talk about what different types of filtering on, and we'll explain that in terms. Think of that in terms of the last slide. You're going to be using one of these three modes. So imagine trilinear filtering, where you're looking at the pixels, 4 pixels in each of your MIP maps, plus you're filtering across the 2 levels, right? So instead of just filtering within a single MIP map, it's filtering across 2. So right, you have bilinear would be in this X and Y direction. Trilinear is because it's going across 2 different MIP map levels there. Now, there's another level of filtering, another way of kind of averaging and smoothing and so on, called anisotropic filtering. The Learn OpenGL site actually leaves this out, and it's something to be kind of aware of as you potentially come across it in sample code. Whether you use it or not, if you're using the older text, it was included in there. It's just yet another level. So if we have loss of detail when the object is tiled because primitives are smaller along one axis than the other, right? So if now suddenly we're tipping things in such a direction that they vanished in the past, but for some reason the horizon is different than how fast things drop off in the distance. Anisotropic filtering mitigates the loss of detail by sampling textures at various rectangular coordinates that aren't square. So it's more expensive. Not all graphic cards support it, but when it does work, it looks really good. Right? So it basically is even one level more context sensitive when it comes to filtering, where it can say, okay, which dimension is this winding up being, dropping off more in, right? So you might see here it sort of uniformly goes to mush immediately here without anisotropic filtering, whereas with AF, it drops off much more smoothly because it can come to those kind of in-between areas where the regions aren't necessarily square. Right? We can filter across non-square things like that. Whoops. There we go. So you don't have to worry about those too much. Those are subtle issues. Right? If you want to make, if you have very low, these days we hardly ever use lower resolution textures, and we have lots of texture space, and we have lots of different models and details there. So those slightly less of an issue. Some other kind of more brute force things that you definitely need to know about, though, and these will come into play usually as a result of kind of UV coordinates not being exactly right. Sometimes you'll generate UV coordinates from a model, your texture coordinates, from some kind of generated model or some solid that you've generated. And when you're doing texture mapping, what happens if you don't have a texture coordinate that's between 0 and 1? Right? What happens when you go outside of that? So sometimes you'll be calculating something, you wind up with a 1.1. Or perhaps you want a repeating texture. Right? As we get into things like materials, you may have seen materials in games and things where you're like, okay, I'm going to use this wood material, and it has a texture map that assigns, here's what a plank of wood it looks like. But then you take that material and you map it, and it applies it across a whole surface, and it's not just one plank of wood stretched out to fit that. Instead, it repeats or something like that. Right? So we have some sort of tiling that we might do, repeating or tiling. Wrapping. So when the texture coordinates go outside the 0 to 1 range, there's still useful things we can do with them. And OpenGL has several options for that. In the case of where you want a repeating texture, you can use GL repeat. So it'll just say, okay, imagine, as far as OpenGL is concerned, that the texture continues to repeat infinitely. So once you get to 1, it's as if you start over again, right? So that your texture just repeats over and over again, and you're going to get that nice repeating value. Or you could say clamp to edge, which says whatever the last pixel that's visible there is, continue to use that one. Or you could say clamp to border and specify a border color for a texture. So the moment you go outside, it basically says, okay, here's some fill color that I use. Like there's a bordering color that we'll just create around that. So there's just three main ways to do things. Either repeating, clamp it to the edge, or clamp to border. There's also like mirrored repeat, where you can like have it flip back and forth. I think this version, I decide if that's mirrored repeat or not. It might be. I think it is. So it's actually kind of facing one way and then facing the other way, and that's because it's mirroring back and forth. Yeah, it's definitely mirroring, because you see as it goes to the top, he's like inverted each time, right? So if this wasn't mirrored repeat, we would just see one portrait stacked all over the place. Where here we're seeing the portrait kind of flipping horizontally and vertically. That's using mirrored repeat for that. So we have a set of functions called the texture parameter functions. This is an extension that says, okay, here's the parameter we're setting and the value we're setting it to. So you can independently tell in the U or V or S. S and T are the same things as U and V. I don't know where S and T crept in or where U and V crept in, but they're used interchangeably. So you can tell in each of the two dimensions how to handle wrapping or clipping, clamping, and so on. Some ways to do that. Start to asphyxiate from wearing the mask too long. There are also some built-in functions to handle things like perspective distortions. It's a little bit like our friend anisotropic filtering there, but a little simpler. So OpenGL will automatically correct perspective distortion as tilted objects are textured in 3D space. So it's going to recalculate along those edges again, depending on the Z, basically the Z position. It's going to do a bit of kind of automatic scaling inside there to change the mapping on the fly. So it's not a filtering, but it's changing the texture coordinates to adjust for that. So that's the quick tour of all of the options. Wow, we covered that in a good amount of time. With respect to, it's not all the options. They're always adding a million more. There's probably, in going through, learning OpenGL, every time I then try to write another example, I went, oh, I could have done that a different way. I could have done that a different way. But those are the basic texturing techniques. In the more advanced stuff, we're going to get into using textures for things like bump maps and light maps and so on. But for now, it's the simple version. So how effective are texture maps? How much do I need to convince you? I'm sure you're already pretty convinced. In what will be the 3.0 version of the sandbox. Let's see if I have. And this was all working right before I got here, so this should be a lot better. The 3.0 version is going to include some more fun things, including texture coordinates and model loading. That's something else we're going to get into next time. And how textures can be, or texture coordinates can be pre-baked into models or not, how they're potentially generated. And we're going to dissect a 3D file format, the OBJ file format. There's lots and lots of different 3D file formats, of course. I'm going to choose a really simple one, the Wavefront OBJ file format, which will give us a fun one to experiment with. And we also will do a generative shape. A couple of different options on that one. So this is a torus. Let's bring that a bit closer to us here. There is a bug on this one. I get to resolve this. The very last set of triangles, my tessellation, some bug in there. We're mapping the RPI seal or checkerboard onto a torus or a donut. It's different than this code's different than the video that I pointed to, where they were just doing a, basically one pixel per polygon in that kind of fun one out there. It'd be interesting to try that. Maybe go into that one. So, any questions on texture mapping? If not, I want to, and I don't have slides for this one, but I wanted to kind of discuss, create a good slide for this. The notion of how to handle multiple models is kind of an interesting one, right? Whether you use multiple VAOs, I talked about that a little bit. Sometimes different people use multiple VBOs and have a different buffer with a different set of coordinates. And the question is, which one's more efficient? Should you have a VAO per model? Should you have a VBO that you change on the fly? How do you load multiple models? How do you change multiple things? And there's a bunch of subtle variations on things, and I wanted to show this one more by example then. So we had a simple quad, right? So I want to look at the textured quad, which is two sets or two triangles, right? So if you have your sample code, you'll see this part in the sandbox where it's basically 4 vertices, each with a position, a color, and a texture coordinate. And then we have a set of 6 indices, 0, 1, 2 for the first triangle, 3, 2, 1 for the second triangle. So what if we wanted to draw another quad or another anything, right? If we want to draw another quad, we could use instancing, which we talked about just a little bit, where if I wanted to, in the instancing case, that's really just changing in my code where I call GL draw arrays, or GL draw elements, either of the two. And I would call GL draw elements instanced. And I tell it how many instances, like in this case I'm just saying, okay, still 1. I have GL draw elements instanced, and I have 1 instance of that. Or I could say draw 2 of them, 2 instances of this thing, but the challenge then is I'm using the exact same vertices and so on, just creating another version. So if I just change instance to 2 and I run this, I still see I just have 1 donut. But let's see if I can do this on the fly. This is going to be a fun one. I'm going to say m not 2. We have that other matrix lying around somewhere. And if I get this right, if GL instance ID equals 0, do that. Let's see, did I get that right? Probably not. Mat 2, Mat 3. Maybe I got that right, who knows? Oh, I did get it right. All right. So what I've done here, I've got the same donut drawn twice, but with a different model matrix because I looked at the instance ID there. So in that case where, we want to, I think it was either said about, a crowd of people that we want to generate. So we can have one model and we can position them all by having a whole bunch of different model matrices, one for each instance of the potential character in the crowd. So that's sort of one way to do it, with the downfall being it has to be the exact same geometry. Right? Still the same geometry. It's just another instance of that exact same model. So let's save that shader. That's kind of a cool one. And the nice thing is if I say, well, I'm going to set this back to instance 1 and just run it again, assuming my shader got saved, it's back to the normal version because I'm only asking you to draw one instance, and therefore GL instance ID is never becoming greater than 0, so it's just one instance. All right, so that's all good, well and good. So what if we wanted to have multiple models that we wanted to draw? The one approach is to say, well, have a different VAO for each model. And so you have a different vertex buffer, a different set of shaders potentially, a whole different kind of pipeline. And that's fine. That can be done. Another approach is to say, well, okay, how would I have multiple models in the same VAO, and that same VBO, and so on? So another approach, which I think I like this approach a lot, and this will be in the second sample. So you imagine we have a set of vertices, a set of indices. Here's model 1, which is just our quad. And we have another quad that we want to draw down here, which has a set of vertices, a set of indices. And the one thing to be careful of is these indices are going to refer to ones in this model, which is actually we're going to somehow figure out how do we load this and this together in the same VBO, but not in the trivial way, which is like, put them both in the same model. Because far more often you can be like, okay, I've got this model that I generate, and I have this model that I generate, or this model that I load, this model that I load, and so on. You're not going to often get them all kind of just glommed together already for you. So this technique still uses a single VBO, right? So we still set up everything normal, but the interesting thing that it does, that you'll see sometimes, and this does kind of come down to how you manage your data with your GPU, is you can say, well, okay, create a buffer over on the GPU, but don't give it any geometry. Just say, okay, here's a buffer over there that I'm going to put models into eventually. You may not even know what you're going to put in there. So maybe just have a whole big size, big chunk. So in this sample, for example, it just says, all right, create an array buffer that has enough room for both of these, but it doesn't load either of them. It just, just says create it with that much room. And it says 0 for the thing to pass, which is, okay, set it up, but don't do anything with it just yet. And then instead of calling GL buffer data, which I normally do, I can call buffer subdata that allows me to put things in different spots if I want. So here I'm doing the simple thing, which is put in the first model and then put in the second model, and then I can ask it to draw both of them. So, oh, well, I got to tell it to draw quads instead of drawing the donut. Quad. So I want to put another quad at a different location that's not offset according to just an index. It's really another independent one. It's using the same texture because it's using still the same shader, and still nothing on that part has changed. But I'm free to add more geometry into the buffer, and I could even make it triple the size, or I could have it put the torus after there and have them all part of that same VBO. So whether or not you get into this, I put this in here out of sort of respect for OpenGL, in that I think every text, every example says like this is the way to do it. And the moment you look at two of them side by side, you're like, wow, they're doing it in like two different ways. Oh, this one's multiple VBOs. Oh, this one's using interleaved VBOs. Oh, this is using VAOs and multiple. And there's no one right way. There's always, depending on the use, depending on what you want to do, is it distinct things. You could even get into things whether or not you use VBOs to represent, like say you have each person in the crowd where you wanted another model matrix for each one of those. Do you use a VBO that contains a massive array of model matrices? You can do things like that. So this weekend I spent a good amount of time like breaking the normal conventions of some OpenGL code and so on. So it's something to be aware of, especially as you get potentially into your own projects. Like, okay, how do you want to do? And chances are a lot of times you'll find like there's some project out there that you want to base it on. So I'll talk a little bit about mid projects and a couple of things, and then we'll probably end a little bit early if you want to use some of the time on the homework. That's totally good. So we have this midterm project, and the idea behind the midterm project is really it's your chance to find something that you want to emulate that combines most of the same techniques we have already covered, which is the basics, right? Get a model, draw on the screen, rotate it around, potentially use, if you wanted to do the planets rotating around the sun, cubes rotating around, triangles rotating around, simple versions. Everything up to, we're going to talk about lighting and materials. So we're going to do a little bit about basic lighting, and that would be everything we've done now, texturing, basic lighting, and we're also going to have these models. So up to here is sort of going to be for the project. Advanced things like shadow mapping, PCF, cube maps, sky domes, environmental mapping. We'll probably talk about those before the project is due, but it won't be due. And the idea, again, some of the main things about this project is I expect it to be that you can use ideas from anywhere. I don't expect the ideas to be particularly exciting, but that you should kind of code it, that you should code it in a way that you did kind of from scratch and understand each of the steps that you made and kind of did it from, from the ground up, rather than big snippets and chunks and so on. So, you can use, basically, it's tough to say, using the code versus, using it from scratch, the techniques. We'll cover different methods for loading objects. The simpler one to do from scratch is the OBJ one, and I'll provide you with sort of a watered down version of that if you want to fix and do more stuff in the project, that'll be there. So for now, I guess the thing I want you to sort of think about is come up with an idea. Look at stuff that's on various tutorial sites and so on, or various demos that you've seen, and say, okay, let me do that one. Try to come up with something that's non-trivial, not just a model, that is involving all of these sorts of things, and that'll be the halfway project. Any questions on that for now? Thinking about it. I don't expect you to have all of it together, but do be thinking about it. How many of you have been kind of following along in the learning OpenGeo stuff? Have you been able to kind of go from there? All right. All right. It's going to be the challenge. All right. In that case, where we are today, given it's 90 degrees outside, well, it's actually not bad in here. I can't really use that as an excuse to say, like, oh, everyone should want to stay in class, I suppose, right? We'll probably wrap things up there. If you haven't already done the homework, feel free to use this time for that, and we'll kind of end things there. Sound good? All right, everybody on Discord, I'm going to end the recording there.